video, no sound, okay, let's do this. So the requirements for this week is it needs to be have a microcontroller, and you need to give the machine a set of instructions, or you need to have something that you can control the machine with. Let's say, for example, a joystick. But ideally, you need to give the machine a set of instructions, or the machine needs to work with a program mode. For example, last year they were making the ping games, the ping pong games, like the pong, sorry, the electronic pong that is the white label. So actually, if you make a device that you throw a ball and it recognizes where the ball and pushes the ball against you, that is also a machine. It's not pre-programmed. It's pre-programmed to actually recognize the machine and go at the ball and go to push the ball. Or it could be something that you can load a set of instructions, aka Gcode in general, but you can make also your own standard. It doesn't need to be by Gcode. And you can make an interface or not. That really depends on. This week is really open. So as long as you make a mechanical electronic mechanism, it's valid. And of course, need to have could not be like completely DIY handmade with cutting cardboard with a cutter knife. Like the point is to use like the laser cutter or the CNC or the 3D printer. Our recommendation is always go to the laser cut and the CNC because they are faster and you don't wait like 20 hours for a 3D printer part to come. Especially like when you have machines, you have in general a lot of components and you will need to print a lot of different parts, and they will take like 1 week to print all the parts. And you don't have time to wait for the 3D printers for that. Luckily, we have a lot of 3D printers. You can send small parts to each one of them and cut faster. So let's go a little bit on the mechanism. We first need to go on actually the degrees of freedom. You want to explain this part, or Oscar? Like we will do the class combined.
Yeah. So okay. So for instance, let's understand that machine a little bit. The one that's So very simply, any machine is going to be comprised of two main parts. One of them, or that one even. First is a structure that holds everything together, and then some sort of mechanism. Okay. Either that one or whatever this one. So in this one, we have a structure that puts everything together depending on the amount of axes, and then we have something that moves. How do we decide what is a structure or what is movement? Depends on what we want to achieve as a machine. If we want to move on one side, on two axes, 3 axes, or 2.5. And the theoretical implementation of that is called degrees of freedom. Basically, you want your structure to not be able to move, so not to have any degree of freedom, and the rest of the machine to have 1 degree of freedom, which means it can move only in one way or in one manner. What does that mean in terms of this machine? Is that with one actuator, I can control this movement. So I need one motor for 1 degree of freedom. I need another motor for another degree of freedom. And I need another motor for another degree of freedom. So I'm able now to move that way, and this way. And this spins this part. Pretty obvious. But what we cannot do is have this motor move 2 things. So we need to design one movement so we need to make a mechanism. In this case, which is very simple, it's just this axis, this threaded axis here that slides in a threaded nut as well, and just moves exactly. So a little bit more like this. This is the concept, right? So we only have one movement, which is this, which is 1 degree of freedom. The rest has to be static. We cannot have this move this axis or this thing move something else. There's no inventions like that, and that's the only concept here. So for every movement you want to achieve, you need to design a mechanism and put a structure around it. And that's it. How do you make that structure? And those mechanisms is what we're going to see today. And how do we achieve different things in the machines? Okay. No hace falta que vayamos.
So it's important that just how we have evolved, most of the movements that we can create are rotational ones. So in general, we have an issue that most of the movements, like the ones that you have here in this axis, are linear. We want to move in a straight line in one axis. And most of the ways that we produce movements are rotational ones. For example, we have the car engines, like the electric motors, they are all rotate, like basically it's a propeller. That rotational movement is the easiest way to produce movement. So in general, we need ways to translate those rotational movements to an axial movement. That is what is in general more useful. For that, we can use, for example, different mechanisms. That here we have a few examples. That is, for example, this is an example of how to translate a rotational mechanism. Additionally, this is how mechanism really used in drawing machines. That we have a motor attached that is moving at gears, and just the combination of 2 degrees of freedom of these ones combined to a static connection in that one, we can actually rotate in different directions. So in this one, we are translating a rotational one in a really complex way of moving in a line. This one is just moving back and forth.
This is called bar leakage.
Sorry?
This is called bar leakage.
Bar leakage? I don't know.
I remember I used this. I did my bachelor's degree.
So in general, we can do it with gears like this one, or use sliders that we basically slide from a really smooth surface. In general, this one is made out of metal, but we have other examples that we can make them through material friction. For example, this is a dry bearing that we don't have any mechanical movement, but we use the friction of the material. Plastics in general have really low friction coefficient, and if you make them thin enough, you can make things slide to each other with a little bit of lubricant. And some plastics, they are self-lubricating too. So that means you don't need it to lube. For example, this one, we are using a little piece of to slide it. We are using a little piece of plastic, that is the white one there, that is self-lubricant. It's a plastic that has a little thin layer of oil that is being separated by the plastic. So actually we don't need to reduce the resistance mechanically. In general, we do that by using bearings that are really complex systems in a really small packages. There are other ways of creating rotational movements when we don't want to have Se ha caído. Esto se ha ido. One second. Because this thing is broken. So in case you want to create an uneven movement, what you can do is not have especially a center element, a circular element. You can have an oval one that is more or less how, for example, like the motors work, depends on the engine, that creates an uneven movement. So in this part, it becomes straight, and then we have one moment that we push.
This is if you look camshaft, it's in all the combustion engines have this on top to regulate how the valves open. And this is like ideally you think that this is going to be pushing or pushed to this element constantly, and then you can define this profile so that has a movement that goes faster up and then slower down, or however you want.
Can you repeat?
So the idea is that you define this profile so that this moves in a, let's say, in a non-linear way from up to down, just like but that's like a certain profile of I go very fast to here, and then this I do very slow, and then very slow, and then very fast. Okay, something like that.
So variable speed, the same as here. You have suddenly like small increments, small increments, small increments, until suddenly like reduces.
Because of the shape of,
Because of the shape of how this of body is defined.
Busca there comes up.
Está ahí, ¿no? And inside, for example, all the engines on the top to actually move the levers on the top, that is the one that gives the fuel and air mixture. There are pieces designed like that. So you have like, depends on the motor, like 16 valves in general, that each one is opens at a specific time. So you can.
I used to have a game that you need to catch some fishes, and each time this thing goes over the fish open the mouth. And
That's
they
true, I do it. Yeah. This is something that's nice to do. Yeah. Same as the, you know, the.
Yeah.
Maybe es una porquería.
Good shades.
Oh, no, perdón. Saiga, ¿no?
Well, but it's up here. It's actually
It's this one.
But at the end, the point here is that you have different ways of moving things. Normally, we're going to be looking at this type of movement because we want linear movement. But in case that you want to create something different, like something that has to open very precisely, or that you want to like move, for instance, I don't know, a syringe or something that pushes something, whatever, you can use this other type of thing. Ideally, what we're gonna try to do is generate some sort of linear movement that basically slides something on top of rails like this one, on top of rails like this, and we have a part, either 3D printed or laser cut or something. But as you can see here, that has some sort of joint with a bearing, and there are different types of bearings, of course. In this case, we have either ball bearings for this type of movement. So linear ball bearings that basically, if you open them, you see that there are little balls inside that allow them to move in a linear way like this one. But you can, if you keep scrolling down. Yeah, if you keep sorry,
The pieces you have on the bike as well, no?
yeah, that one. So a type of bearing at the end is what we have in here, but that we can replace it for something like this, which is a self-lubricated plastic, as you were saying before, that doesn't have friction with respect to this. Important thing is that, as you can see, this thing and this thing are very shiny because they are quite well polished and they don't have friction, a lot of friction. The same, so that this movement is somewhat smooth. Like you don't want to put a lot of effort in here to make this movement. So you have a part that is very well aligned, and that is something that you'll have to deal with very likely in your machine, that this part is aligned or that this is aligned properly so that your the part that you're trying to move doesn't have to turn or do weird things. Okay.
So why we want to reduce this friction? Because if your motor needs to spend half its power just to counter effect the friction of the sliding surface, you only still have half of the power left to actually move the object you want to move. Could be, for example, a CNC motor, or could be a 3D printed head, etc. So in general, you want things to be as light as possible, but still the strong as possible. And exactly is the opposite. So we always have to find a balance between friction and accuracy. The more tight accuracies you have in your sliding elements, it means smaller movements you can create. Let's say, for example, the micro milling machine, all the pieces are really tight to each other to kind of reduce the little movements that you might have. That increases the friction. So that means you are spending more energy in actually moving just the machine itself. So that's why, for example, it's more difficult to cut stronger material with the small ones, because they are meant for like accuracy. Meanwhile, the big one, that we don't need that much of accuracy because we have big gear components that are really heavy and we are working with higher tolerances. We have still stronger motors, but we don't spend most of the energy in moving the machine. We just spend it because we need that strength to actually cut the material. How to reduce the friction could be done by the materiality or can do by mechanism. For example, the bearings are mechanism. So basically we have millions of balls, imagine like millions of small wheels, omnidirectional, that basically they rotate. It's the same as if you feel a flat surface with a lot of balls and you put a platform on top, you can really slide on top. Well, it will be the same if you have two like plastic surfaces and everything is full of oil. It's sliding. So the point is to reduce the friction in the way we can.
There are like a specific, I don't know, ways to calculate the relationship between the friction and the power, or what's, you know what I mean? Like if you want to move a motor on this axis, but there's a lot of friction, and you want to know exactly how much friction you need for it to move smoothly and not just flat. Is there like something specific to?
No, actually, you never want friction because that's, I mean, it's going to generate heat and it's going to wear your axis and everything. So the least friction you can get, the better. And that's why you have to lubricate things, you have to do maintenance, you have to either do alignments of things, etc.
And replace components.
And replace components as well.
Replace components.
But in general, I mean, there's no too much friction or too little friction, let's say. At the end, friction is not something that helps you in general, unless that you're using, for instance, like a belt, like that we will see later, like the ones that we use. Well, not in that one. That machine doesn't have an actual belt, but some of the machines here use belts for achieving the movement, not timing belts, but like normal belts, and then you want friction. But it's because the way the mechanism works. But in general, for this type of accesses, you don't want it.
And if I understood correctly, this question, for example, you have like this sliding one, let's say you have two pieces of plastic. There's a way to calculate how powerful it has to be the motor in order to move that kind of.
You could calculate that.
It's just like
you could calculate that, but in general, it's a theoretical calculation. Imagine you need to know exactly what this surface is in terms of finish. If there's any sort of lubricant, if what play do you have in here, and that is not going to be an easy thing to calculate. So you normally do experimentation. You take the motor and the power supply, and you see for whatever amount of movement that you are trying to achieve, you see how much current you're drawing. And if that doesn't, if it's too much current, then either, so if it's over the specs of your motor or your drivers, or you never achieve the actual movement that you want because, for instance, your electronics are limited in terms of current that they can supply, then you either need to reduce the friction, or if you cannot do it, then you have to increase the size of the motor.
So it's always better to refer to the electronic bit of things rather than the physical bit of things.
And more than in the experimental way of doing it, but rather than the theoretical calculation. It's going to be really complex calculation that is, I mean, we could approach it with some sort of models or certain calculations and things, but it's never going to be an easy thing in this setup, let's say, in the Fab Lab environment.
Like manufacturers of bearings, they give you like friction per square centimeter and this kind of values, but it's not only about the bearing, it's about the surface, what is the temperature of the surface to actually, so the models are quite complex to calculate. So in general, like you have like, say, industry standards that are guides based on the motor. For example, if you want to build a machine like that one, you need to know automatically that you start with a NEMA 23 at minimum because of the torque that you will need. So it's also for the application. For example, between that machine and that machine, actually those machines, like the Ender 3s and the Krakens, it uses the same kind of bearing, same kind of mechanism, and same kind of actuation. But just because of the size of the elements that you move are triple size. So actually it's automatically next motor range because you need just to move more mass. And that, you know, in general by experience and like I'm checking other designs.
Yeah, by reference.
And references. So how to translate rotational movements into linear ones? For example, in here we have the pistons of a motor that, as we said before, is an eccentric axis. So this axis, we have this main shaft that is making a movement like this. It's not a straight bar. So when it rotates, this is the rotation. As it's out of the center, it's pushing some elements and different timings. Will be the same as this one. Oops. This one, but imagine that you multiply these elements by 20 on the side.
Yeah, and
So,
they're not in the same line.
and not in the same line, exactly. So this is actually, for example, how like gas engines work.
But why do we need that? I'm not saying explain to me how an engine works. I'm just saying why does it not need to be
At the same time.
Hmm.
In a simple way, if we have a rotation, let's say, and we push in this point, the rotation is going to move until here, and the rest is going to be inertia.
Okay.
Like basically, if you have a cylinder and you are pushing the cylinder, if you push forward, it's not going to create any movement. So as long as you are, let's say, in this area, this is the only area that actually your push is going to create a little movement. So imagine that you have this sphere and we basically divided in 4. So we need to push here, here, here. So when this rotates, then this one, that is number 2, pushes. Then this one, it pushes. So we need to do ta, 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 ta to push. So actually, that's why the motors, they sound, if not, they will be like boom, boom. Actually, some motors, like especially in cars, we don't see, but in motorcycles, maybe you have noticed that some motorbikes, like some pop, 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 other one pop, 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 is because of the amount of cylinders. That's not exactly, it's about the amount of cylinders. So for example, the super high speed motorcycles, the racing ones, there are 4 cylinders because they give smoother movement. But also implies more bigger motors, etc. So for example, in off-road that you want something light, you only have 1, but that means also the push is not as consistent. Okay. But yes, you are like jumping and everything, you don't really care. But he knows way more of this. So basically, as in the moment that we are out of this area in the center, we can, even if we push, we are not getting any movement. And basically what we get here is a explosion that pushes the cylinder down.
At the end, just remember that in this concept, what we want to do is transfer something that is a rotational movement into a linear movement, or vice versa. Either you, and this is a lot, this is done a lot in combustion engines, but also in compressors. Combustion engines, you generate an explosion on a chamber that generates a linear movement and then rotates. A compressor is the opposite. So you have, exactly, but in a compressor, you actually use rotational movement to push into a piston and compress air for a certain amount of time by reducing the size of a chamber with a linear movement. Why do we use a linear movement there? Because it's just simple. It's simpler to encapsulate something in a cylinder than in, for instance, in a weirder shape. Because in a cylinder, you just can put like this bottle, like a joint or something like that. Then if we want to transfer, and that is not normally what the type of machines that we're going to be doing here, but if you go back to the mechanism, so if you scroll, then normally the type of things that we're going to be looking at are more either gears, like this one, that try to convert rotational movement into rotational movement, like these
in a
two,
different axis.
in different axes, exactly, but that they don't even have to be aligned. So there could be, as we will see down, like some conical ones that can transfer from in angle. But if you scroll back up, basically what we try to transfer is rotational movement into rotational movement. Not only because we have, let's say, a geometry constraint, but also because we want to increase, for instance, the amount of torque that we're giving into something. The amount of, so in this case, we have normal gears in there. The idea here is that you have this motor with a very tiny gear that moves into a very big gear. Why do you do this? Because this one has a certain amount of rotational force, let's say, or we call it torque, that is not going to be able to move this, what we have in here, this piston that normally has compressed air, or compressed air and a mix of clay and these type of things. So you put this big guy that basically is going to convert high speed, low force into high force, low speed. And if I rotate here, you see that this one spins faster, of course, by every tiny move that I do here. If I do the opposite, I have to spin this much faster, but by a small force that I apply on my right hand, this one still spins. It's very difficult for me to stop it because I'm increasing the force that I have in, like the rotational force, by the relationship of the size between this and this. And if you scroll down a little, you can do this with different sizes, or with the same amount of sizes or different sizes. But at the end is a matter of having the relationship between how many teeth this one has versus this one. Okay.
When teeth is like basically is the outer diameter. Like we could have bigger teeth or smaller. It doesn't matter. It's about the difference in diameter. For example, this is a 1, 2, 4 reduction. That means for one rotation of this one, full rotation, we are making 0.25 rotations of the bigger one, but the torque we are multiplying by 4. So,
and that way you don't need to have a giant motor. By the way, just one comment. We normally refer to electric motors as motors and combustion engines as engines. In Spanish it's the same, but in English we say it that way. And with this, you see that there are different types of motors. This is not the same type of this motor. We will talk about them. But normally we just refer to all electric motors as motors. And in particular, this one is a stepper motor. And this one is a DC motor. We will see that later. Just
DC motor?
This is a DC motor. Actually, they are both DC, but this is normally called DC motor, and this is a stepper, or this is a stepper motor. Okay, but we will talk about this in a second. Then the next type, if you go a little bit up, is not that much, electrics. ellipse. Right? Is this type of gear is the same as this, but there's an angle. But instead, you see that these ones are straight in here, like the teeth are straight, they are vertical, and that one they have an angle. That is done so that you can reduce noise and increase the amount of time that the teeth of these ones and the teeth of this one are in contact by increasing the surface and also trying to reduce how fast or how sudden the contact is. In a normal gear, they go like this. And in this type, the movement is more like little by little. So there's less noise. And in this case, the geometry is much more complex. You wouldn't do it in this case unless you download that design for someone else. You can try as well to do it, but it's going to be a little bit more tricky to design. And you see this type of relationship between the or the reverse gear. Reverse gear is a straight. So when you put reverse in your car, it's a straight sound, and that's it normally sounds like because it's this type of other, and the gearbox normally sounds a little bit more in reverse in like say normal people's car. Like expensive cars, they also put LX gear sound either, but in normal cars, like car rallies, all if you look at the inside videos, it's all the time like whoa, because they use straight gears because they're slightly more efficient. They don't care about like conflict. Class that doing slowly, like in the let's say slowly, have more like you start touching a little bit and they increase and you decrease. So actually that produces low power losses compared to straight touch. Okay, so what else? Wait, espera. Venga. No sé si sigue. Hello? Yeah, you see us? Perfect. Like we just changed the network. Let's change the screen again. Okay. Okay. So that was for parallel axis. We want to translate the movement from one axis that is rotating into another one that is rotating. And you can do with different ratios, let's say. Increase the speed, reduce the speed, etc. If you want to do it in this type as well, instead of the them being parallel, you want to transfer rotation from here to here, you can as well. You have to do conical or bevel gears. Okay. The combination of both is, or the helix gear and the bevel gear, that is the silent version, let's say. And that you find in a lot of cars as well, because they're used to transfer, especially I make a lot of references to cars because I was, like, as Adrian, working many times for a long time in the car industry. But basically, if you have like a rear traction car, like that has the engine on the front and the traction wheels are in the back, that type of mechanism is found to transfer the movement from the front to the back, so that the axis doesn't go inside of the cabinet, let's say, because you can put the axis really low, almost touching the floor, almost, and doesn't have to go inside. Then this is another thing, but you can see that bevel helix gear in there, and also something that I think is a little bit more advanced at this moment, but that is a planetary gear that basically allows the wheels to rotate when you're turning at different speeds. So imagine your car that is going and has one wheel here and one wheel here, or 4 wheels, but when you're taking a turn, this one has to go faster than this one. So that mechanism allows for that to happen. But it's called differential, but don't worry about now, it's a little bit like, if you want to show it.
No, es el video de referencia. Referencia Chrysler es que tiene un...
Sí, es el antiguo este.
Sí, es el mejor video del mundo. Okay, if you're interested about how actually this guys works, there is a video from the 50s of Chevrolet or Chrysler that is amazing. Like, and it's like a 3-minute video or something, like 9-minute video. We don't have time, but they explain like really with the stick models. Actually, it's from the 37, super old. But it's one of the best videos on actually how to explain how this mechanism works. And they start with simple sticks, and then they increase slowly to show how they work. I will copy in the chat in case someone wants to see it later.
Maybe it's in.
So
Okay, so that's for gears. Then this one is also very common. It's called pinion rack mechanism. You will transfer, again, linear movement or rotational movement into linear. You find that in the Raptor, for instance, in the big machine, the x-axis, well, actually x and y-axis are the one with this. The rack is, let's say, the horizontal part, let's say, a straight, infinitely long gear, and the pinion is the rotating one that normally contains a motor in there. And if we will go later to the Raptor and we'll see a little bit how it works, but basically it's the same mechanism as that.
So usually you use this kind of mechanism where you need to move like high mass or a really heavy duty mass. It means you need to move a lot of kilos, and you need also like strength to move them. Not only you need to move something that is heavy, but you need that movement cannot be retained. That means with the motor you can move it, but without the motor it needs to keep the position locked. So that doesn't mean that if, for example, we tilt the machine a little bit, the machine will automatically slide down. We need to lock the position in place when the motor is not pushing. Let's clean all drawings. Let's go down a little bit. We have the planetary gears. That is.
Yeah, that this is a little like more complex. I recommend that if you want to have a look at some videos of these things, but basically it's a mechanism that combines 3 movements, well, 2 movements of 2 steps of gears, and that by fixing certain or putting certain constraints on the different components. Imagine the blue part is fixed right now, so you achieve the movement of the axes of the small gears versus the big one, or you could fix different things with respect to that. It will achieve different torque ratios or speed ratios, etc. That is a little bit more complex, but it allows for a lot of flexibility into the same mechanism to just block different things with a clutch or something, and then to have into the same mechanism different gear ratios or different conversion ratios, let's say, from the input to the output. At the end, remember that what we're trying to do is convert one movement on one axis to another, and this is just a way of packing, let's say, a lot of or some possibilities into the same mechanism.
So, for example, this is a stepper motor, and this is a stepper motor with the planetary gear inside. Instead of having a lot of external gears to reduce, because this is basically we want to increase the torque, have the same torque, have more torque with this, but with the same motor, but a slower speed. So instead of having a lot of external gears in that take huge space, with planetary gears, we can reduce it to a really small package that is adding, like in this case, like 1.5 centimeter, and reduce it. This is a 15-to-1 reducer. It means this motor rotates 15 times slower, but 15 times more torque than this guy. That's huge change for in a really small space. So planetary reducers are using to have like high reduction with keeping lot of torque in small packages. Actually, inside all the robotic arms, they have at least 2 or 3 of these guys inside each motor, because with all the arms, all the twists are done with motors with planetary reductions.
The lab, you have something to make gears apart from the
No. Well, you could make some gears on laser cut
CNC.
or CNC, but they're not going to be, I mean, unless we make them on wood and then you polish them, or acrylic or plastic, like HDPE or something like that.
This one, for example, these ones are printed or?
These are 3D printed.
This one is 3D printed, and this is a pinion rack. Actually, this is the motor and a rack. You can see a little bit. You touch. Maybe
So it's possible from the time you buy it.
here. I have made in aluminum. Like it gives good result, but you need to be really careful while milling and use really small endings. This is a mix of 3D printer and CNC for acrylic. The rack is being acrylic and the jig is 3D printed.
The gear, though, if you 3D print it, it's not the best option because
Yep.
it has a lot of friction, and you don't want that. You're gonna wear the prints very easily. If you want to do actual gears, either we buy them, we can cast them, we can mill them in plastic. We have some bits of Teflon or HDPE that we could use, or for certain like low power application, you could either cut them as well, laser cut them.
Yes, everything depends on the amount of torque that you're applying. For example, I can show you then, like the extruder I was making, like I'm using the biggest NEMA on the market with the biggest reduction, and it's actually like exploding the 3D printed parts, and they are casted with epoxy. That is like a super strong glue, and it's just tearing them apart like it was butter. And then we have the chain that is while you're using engines,
Yes.
also like in your bicycles.
So they can pull up and touch it.
Reconnect. Just for the week.
Yeah, so belts, belts, you see them every day in bicycles and motorcycles, things like this. Why do you want to use belts? They're not the best.
Vamos a conectar el tema aquí porque si no se va.
They're not the best for, let's say, noise, friction, etc., but they allow to save very big distances. So you might, let's say, like in your bicycle, you need to move something from here to around here. You will need to transfer the movement of your pedalier into the movement of your pinion in the back of the wheel. You use a belt or a chain to do that. If you need both things to be synchronized, let's say, so that the one turn in here implies always the same amount of turns on this one. It can be 10, it can be 1, it can be whatever. You use a belt, a timing belt, or a chain. A chain, as you see up there, the chain, the normal one, is very noisy, requires maintenance, and the setup is not as simple, although you find them everywhere in bicycles and things like this. A belt is, and also a belt is a solution that allows you to absorb some shocks. So the belt is made, the one below, is made out of a semi-elastic material. It has rubber, it's basically metal threads with some rubber casting around them. And it allows to absorb some of the shocks that you might have because you're braking on one side or because you have sudden changes of movement and things like this. You will find belts in a lot of machines, especially timing belts. Just scroll down a little. They are not as efficient. They are not as efficient as chains because there's always a little bit of loss in the friction process that from one body to another. But they allow to transfer. So in terms of power efficiency, no. but they allow to absorb some shocks. Also, if you see, I think you have one there. If you need to transfer movement from one axis to another, and you don't want to use a chain because it's noisy, because it doesn't absorb the shocks or something, then you can use a timing belt, which is a belt that has teeth and that basically synchronize both axes. You see those in the big Raptor. You see them in this machine as well. They are a little bit hidden, but they are there. And these ones are different types. And yo no me sé la nomenclatura exactamente del GT2.
Yeah, there are different sizes and they have standard GT2, GT6, GT8, GT12, GT20. Depends on the weight, the amount of load that they can carry. So, for example, these ones are quite easy to determine. If you need to pull 20 kilos, you need a belt that holds at least like 20% more. So you dimension based on that. Also, they are made of different materials. Some of them, they are just rubber with fiber. Usually it's like glass fiber lines inside along the length, yeah, to make them last longer and also to don't elongate and break on tension. Some of them, that depends on different quality. They change also the type of rubber they have, like low friction, higher friction, depends more on heat resistance. Also, some of them, for example, there are Kevlar. This like super nice type of, it's similar to fiberglass, but it's way more resistant and elongates less. So, for example, why you will say if this is more comfortable, why we don't use this for everything, etc. For example, a bicycle. First, you cannot change gears with a belt. You only can have one relation. Even so, some bicycles they only have 1 year. For example, if you just have 1 year, a chain mechanism has a power loss of around like it's efficient up to 99, 98%. You only have 1%, 2% of power loss with a metal chain. With a belt, it's 3, 4%. It's not a lot, but it is. What's a good point and why it's good to use belts? They almost have no maintenance, like at all. And the life length, don't have maintenance.
Well, you have to tension them. So you have to like, if they lose tension, you have to either like re-tension them, so put them tense so that they don't like have too much slack. But maybe you even have to replace them sometimes in case they got worn out. But they mostly don't have.
What do you mean by they absorb the shocks?
Like a shock. Like if you imagine that in a chain. So go up. The chain only works as if you see in that image, the part that is in tension is the top part of the belt of the chain, sorry, and the bottom part is loose. Okay. The top part doesn't have any play. Let's say so. If you put a shock, like if you do a sudden movement on, let's say, the pedalier in the case of the bike, like boom, like very sudden, it doesn't absorb it. The chain just transfers the movement from the pedalier to the wheel, and it all goes as a sudden shock into the wheel. In the case of the belt, some of that sudden movement gets absorbed because the belt is flexible. Yeah. So
basically, as the chain is metal, it cannot elongate. It's like a leaf. It's not rubber, so it keeps the same distance. So all the like sudden action is transferred. Meanwhile, the belt, even if it's as reinforcement, it still elongates a little bit. So actually, that is absorbed by the rubber of the belt. For example, to give you an idea, a chain, I know because I've been looking a lot of this week about it. Chains in a bicycle, they last around 10,000 kilometers. Belts, 30,000 with no maintenance. So basically what determines the belt is about the length and how the rubber gets wasted. And usually you have mechanism to make the tension increases. So usually you have a third wheel to slowly increase accommodate the elongation of the thing. Happen the same with chains. Also chains also elongate because the bearings inside the little knobs get wasted, but they have higher maintenance. The good point is chains can transfer like way more heavy loads. For example, in car engines, like the more, let's say, don't know. The more sensible parts, usually they are prone to use chains. Meanwhile, the fans that if they break or something happens, it's not a big deal, belts. But that's not completely like that.
So normally now, for instance, what we were talking about earlier about the valves in an engine, if right now all passenger cars use belts, timing belts, they're cheaper than chains, they are less noisy, and the technology now allows for a belt and that can transfer the timing properly so that the valves open at the right time and everything. But you have seen that many times you hear it even on your car, or that you go to do the maintenance and they tell you, no, we have to change the timing belt. It means that's the belt that is like the one below, but that has this little tip. And they have to replace it. But it's normal, it's very common nowadays as well. In bigger models or bigger engines, sorry, like I don't know Ferrari, but a big engine normally uses chains. Big diesel engines like Fards or things like that.
We can use time belt for precise things like PCB, stuff like this.
No, they use.
It's precise enough.
Yeah. So normally you will. Now comes to the point. Go back to the mechanism. Okay,
Some comes.
that comes. Okay, so now we are at the end of, let's say, movement part, right? We didn't explain this type of mechanism, but basically it's the stepper has a collet that joins the stepper motor to this threaded axis. And you see that the pitch of this axis is very small. So the amount of turns that we go per, let's say, meter is very high. Why do we want that? Because we want to increase the resolution of this stepper. So for every turn that we give in here, the amount of movement that we make this way is very small. So if we control one turn in here, maybe this moves, I don't know, 1 millimeter, 2 millimeters, okay? But on top of our capability of moving this very precisely, increase the possibility to make small things like PCBs. In a larger machine, for instance, well, imagine this is very expensive, right? As you can imagine, this is machined, this is like very precise, it's not cheap. In other machines like 3D printers, that machine over there, some of these machines over here, they use belts. What do you? These belts, for instance, in this one, these are the timing belts. We have a pulley in here on top. You have a pulley here and the stepper motor down here. And this is the timing belt that is attached to this part. And then here you have a rail with a bearing. And in this case, it's a linear bearing that stays on the rail. In this case, this other machine has the same as that one over there. And mostly all of the machines, yeah, we could say that almost all of them will have this type of mechanism to move this link, to make this linear motion. Why do we do that? Because we have very precise control on this type of models. And that brings us probably it's time to introduce these things.
Yeah. So that's, for example, that's one of the approach of machines. Like nowadays, maybe you have seen some Kickstarter, like this kind of thing. They say, hey, make that your 3D printer a CNC, or make your CNC a 3D printer also laser cut, like 3-in-1 machines. That's good, but actually that's staying in the middle of nowhere. Why? Because from a basic design point of view, you want to go either accuracy and torque, or speed and accuracy. In general, you always want accuracy. So it's torque or speed. If you want to be fast, you don't have torque in general, because you are using the motor to move at really high speed. But that means if you move at high speed, you need to be lightweight. Lightweight means reducing the amount of motors or the size of the motors. The same that if you're running in the middle of the nature with a 50 kilos backpack, you can't go really fast. Meanwhile, if you just have a water bottle of 1 kilo, you can run much faster, no? Happen the same with the machines. Machines that are meant to be light, they're meant to be fast. For example, a 3D printer. Why? Because you're basically not moving a lot of mass. You are not pushing. You are just basically throwing plastic or liquid or a laser. It means something that is almost immaterial, doesn't have a lot of mass. That means you can move really fast. And you want to save time because you need to still make a lot of small movements and you want to do as fast as possible. Meanwhile, a CNC, on the other hand, you want to mill aluminum, you need to have a really huge motor. Actually, you want to have the biggest motor as possible, and you want to have as much torque as possible. You cannot be light and strong. Like it's a no. It's physics are there. Like you have mass and inertia. So with CNC, you want to go with bigger motors and have mechanism that doesn't allow you to lose steps. For example, gears, like linear axis. How do you call it? Threaded rods or ball bearing rods. So for CNCs, for machines that need low torque and force, it's always usually threaded rods or ball bearing rods. Meanwhile, for machines that are light and you want to move fast, you use wheel, pulleys, belts. Maybe some of them change, but in general, not that much. So from the start, like the base core of the machine, how it's designed is completely opposite. So as a 3D printer can mill, yes. Will be strong? No. CNC can 3D print? Yes. Could be fast? No. Because by using these threaded rods, basically what we are doing is using a reduction. For one rotation, we are just moving a little bit. So there is a moment that we cannot rotate endlessly the motor. The motor have a limit on the speed. Usually the limit of speed could be 300 to 3,000 revolutions per minute. If you rotate 3,000 revolutions per minute and you're just moving 10 millimeters per minute, you can go really fast. Meanwhile, making this movement with a belt, you go really fast. So that's a basic. First is when you design machines, you have that deal. What you choose, and based on that, you start growing on top. The size of the motors depends on the strength you want, etc. For example, these small machines, we need strength. Yes, but using automatically the thread rods is augmenting the strength that we apply with whatever motor. So actually, we can reduce the size of the motor because we don't need that huge motor for such a small machine. We can put a way higher, bigger motor in this one. Yes, in that case, basically what we are doing is upgrading. Now we can cut steel because it has more torque. So there are some machine designs that are more prone to be fast, and other ones that are more prone to have torque. And that's a huge difference in general between 3D printers, lasers, and CNCs. For example, laser is also really fast. You have seen the laser cutter moving really, really fast. Why? It's only moving a small mirror.
There's no contact as well.
There's no contact as well. So actually, the limit there is actually mostly on the software and how you manage accelerations and speeds, and a little bit of mechanics on the belts. So for example, laser cutters are light, they don't produce no noise. It's the fan what makes noise. Why? Because belts, because it's smooth, and the belt also accommodates the small elongations, etc. Then we have cams. We don't need to go too much on this one. No. Bearings, type of bearings. We can divide it in three types. We have linear bearings. That means it's a cylinder, and we push a central rod. We have, this is a aluminum rod. No, this is a steel rod of 8 millimeters. And this is you see? Ooh. Why? Because we have a lot of balls that are making the circuit. So basically, when the first ball that is here is moving to here, and inside there is a loop back for the hole. So actually, the design of this for the size is quite complex.
So the balls are moving.
The balls are moving. They not only rotate, but they also move.
Actually, they have like a small channel, and they go. So It's like they go inside a small thing that, and they push one another, and they go linear. Like this,
Animation. Yeah.
Something like that. This has the format more like that one.
This
One
one
is more or less the same.
exactly. They could be square or round. These ones are round. Sorry, square, but it's the same concept.
So,
It's not a good animation. I know this. There is another type of bearing that is called ball bearing that is also, they usually have animations.
the bola sucede.
¿Cómo se llama el de esto?
One is linear.
Sí. No.
This is weird because I feel like now YouTube has become more like a platform for companies to showcase
Yeah.
rather than actually people putting good content.
Ball screws, sorry. Because ball screws, they work in a similar concept, but not exactly like that. Okay, so inside the threaded rod that we have here, we have the dry version that imagine that is tilted, threaded with a nut. The upgraded version of this guy is the same with bearings. But the cost of this, for example, for this case, this one is an industrial one. This is around 30 euros. The ball bearing of this is 150 euros as minimum. And because it implies like a really well machined manufacturing technique. So basically, it's the threaded rod, and inside it's not a simple nut. It's a nut with a lot of balls rotating, reducing the friction of the thing. For example, we have a machine here that has this guy. I don't remember which one it is. Tenemos uno de estos. Creo que es el eje de la presión. La Z. So basically, as long as rotating, instead of having like a metal to metal friction, we have metal to balls to oil to metal. And inside all this chamber, this is usually also filled with a lot of oil. And you have some screws that you need to open for maintenance, fill it with grease with an injection, and close it. Then these guys are machined to an accuracy, like if you make the ball roll, they have a microns accuracy eccentricity. That means they are completely flat. So usually in general, now like you can find them copies, like with lower quality. It's affordable, like 300 euros, but good ones are really expensive.
Usually what they're used for.
This is for having this, the same, but in industrial quality.
In what, sorry?
It's the same as this one, but in industrial quality.
Industrial.
Like you increase accuracy, reduce the friction. Yeah, it's the best. Actually, for example, when you have a problem with these guys, that is called backlash. I don't want to get too crazy into this, but okay, seguro que hay una forma. Threaded rod backlash. This is the nightmare of the machines or threaded rod design. Yeah, here. So you have a threaded rod and you have a nut. You need a little bit of tolerance so it's able to rotate. That tolerance, that means when you're pushing, this side of the nut is touching. But when you change the direction, it changes from this side to the other side. That means we have like a 0, 1, something, depends on the tolerance of not accuracy. If you change the movement, but the machine takes time to react because you need to change from the side of touching. That's called backlash. And actually that's the nightmare of accuracy.
That's the one, sorry.
Nightmare of accuracy. So this one you don't want this. You want to avoid that all the cases. So actually how you design the nut, you have designs that are like a double nut. Devices usually they are double nut with a spring. So one side touches one direction, one side touches the other, and we have a spring that accommodates that movement.
But that's within what?
Within threaded rods.
Inside?
Like the nut that is going through this little teeth has this little movement.
Okay.
Actually, here, in this guy, and also here, here we have a nut, here we have another one, and inside this one we have a spring
Okay.
to push it. So it's a backlash reducer.
Okay.
But this is like, it's a good solution, but it's cheap. Like we cannot go to microns accuracy with this machine just because of that. Because we are not using also because this is not perfectly machined to microns accuracy. What's the difference between a ball bearing like these guys? To reduce that, actually you always touch all the sizes, all the time, all the threads on both directions. How you do that with balls? So you have constant contact everywhere. That's why also these guys are more expensive. These and these are the same, but the minimum size you get these guys, and how they look usually is like also way better.
Technically, this one that was on the screen, it doesn't have backlash because it's the.
No, this one doesn't have backlash.
Because of the balls that are moving.
Exactly.
You don't have to pieces. Okay.
And for example, 3D printers doing is these guys because the cost of one axis of this is the same price as 2 3D printers.
Yeah.
So they use a threaded rod with a normal nut, and the first upgrade that you can make to these machines is anti-backlash nut.
Okay.
Just change the type of nut that you use. If you have money, choose one of the ball bearings.
Yeah.
Say that, for example, like good FDM 3D printers in the 5 to 10K range, FDM 3D printers, one of the difference will be that the axes are ball bearings. That means also no maintenance or reduced maintenance because these are, you are working with teeth, they have friction metal to metal, the nut wears off, you need to replace the nut. Okay, so we have linear bearings and we have ball bearings that is to accommodate a cylindrical movement inside another one. So we have here, we can clearly see here the little balls rotating.
It's the same as you have in the bike or no? But
Yes,
smaller.
exactly. So you have something that grabs and you have something that rotates freely inside.
In this case, sorry, you find it in here as well. And this is casted in there. So you imagine this motor here with this threaded rod. And then in here, you have to, like, if you don't do that, the axis is going to be like just hanging from one side and then might bend if you put a lot of load. Exactly. So this in here just gives a little bit of support, and you do that. You have to allow this thing to still rotate with respect to the frame, but you want to support it. So you put a bearing in there that basically allows both surfaces, outer and inner surface, to move relatively or rotate.
Bearings, they come in multiple types. For example, the one that you have on your hand right now is a dry non-metal bearing. For example, that one is used into chemical environments or water environments because it doesn't have metal. It doesn't like get rusty, for example, or these are really oily environments. You have open bearings, you have closed bearings that they have like caps here that they protect. They have multiple great type of bearings. For example, closed bearing. And you have like for water environments, for oil environments, for like heat environments, for cold environments. So this one basically they change like how the cage is, what is the material that holds the balls composition, the metal that makes the outer shell, and the sealing rings. And they have a lot of types. Then we have cylindrical ball bearings that they have not have balls. Basically, they have cylinders.
Balls.
Eh?
They don't have balls.
They don't have balls. Usually, it's like for like loads that they are really on the center of the ball of the bearing. They don't have side forces. They cannot afford because basically they are rotating cylinders. These ones they have like usually for heavy duty transfer loads, something that is really heavy.
Why not? Sorry, why they don't have balls?
Because a sphere has a small touching area.
Okay,
A cylinder has a huge touching area. That
Okay.
means it's able to transfer bigger loads
okay.
from the outer to the inner case.
Mhm.
Actually, they look like this.
Yeah, crazy. 160 euros per unit.
Oh,
Sorry,
sorry.
I just.
Yeah, well, this
Like-
one is huge. This is like this.
Like this. Okay.
But yeah, good bearings could be really expensive. The flat ones, the needle ones that are like cylindrical bearings, and then we have conical ones that are tilted that accommodate forces between actually to don't let an element push in the axis. So you have, I don't know.
So imagine that this when you push, imagine that when you push here, this was like being pushed that way. So that this doesn't move, or that so that this controls a little bit, and this doesn't. If we fix it in here, then the motor will end up that way. So we put one of these, so that it controls and stabilizes, let's say, things in place.
This one, the
The
conical
conical
one.
one, yeah.
Okay.
So it allows rotation, but also keeps things in the center. You have this in compressors, and
But how come it keeps things in the center? I mean, the thing would be in the center of it.
because basically imagine that this is the cone, and you are rotating here, but you are pushing to one side. So your basic structure just holds things here, and then by the fact that you have this angle, it's not like this could slide inside of your structure, but it has this.
Because it's like, okay.
It's a cone. Yeah, it's a cone.
So
Exactly.
if you push in this direction and you also have like load because you are basically, that's why you have a cylindrical bearing, like a bearing. How to accommodate this without making the, let's say, the balls, in this case, move out. So basically you need to tilt this surface, contact surface, to counteract. So you have the cylindrical roller that is pushing in the one direction, and your element inside the element is pushing in the opposite direction.
Cool.
Then we have clip strings.
They're just retainers, so they avoid shafts like these types or these types if they have any sort of movement to the side to hold bearings in place or to hold the shaft in place. You normally need to put like a small space for this to go in, and they are like this one inner clips or outer clips, let's say, but exactly. So that's your shaft, and then you put that in the middle so it retains the shaft and doesn't move away.
So you put it through, and you have it's opening one side, so you can open to click around.
And how do you close it?
You open it with pliers.
It's opposite pliers. It's a plier that when you push, opens.
Okay.
More or less like it's not like this, but you would like.
So
you put it in, and basically, but there's a different type of pliers that instead of when you do this, it closes. When you do it, it opens.
it opens. Okay.
If you don't do with the proper tool, usually it's a nightmare to pull them on. I mean,
It is a nightmare.
because they are quite strong to keep things in place. Then we have mechanism, locking pliers.
I mean, this is just a lot of mechanisms. We don't. I think we.
The first plier is the one that you use to change the gas bottle, or no?
The gas?
gas.
There you go, the gas.
This.
Yeah, nothing, it reminds me of my childhood, we used to change the ovens.
This is just like,
And sorry, I don't remember, but
I don't know how you call this in English, but it's just like a
Locking
locking,
pliers.
it's that you close them and they stay in place so that you don't have to be pushing, like closing like this, and then
and then you do.
and then you can just move like a lever movement to open something that is really tight. But the mechanism is the interesting part. So,
Yeah, the spring here.
and then you release, you can adjust the force of that spring with the little.
With the little thing in the bottom, no?
Yeah.
Technically, you need to open it for it to be stuck, for it to lock.
Well, and you can use, you see the tiny
Yeah, on the
little
left.
finger that is on the bottom, you release that when you want to, so you tighten and then you release it.
No, I think this is the one.
One of the
The
principles
mindset
that I
it
would like
was.
that I would need to use in the. in the heat- in the
At least
heat
I have
transfer
a
from
lot of
Then we have well, type of machine. That's when we can go for the machines
I
and
think
have a break.
this is just some references.
Let's see some machines. I will connect with my phone.
Maybe we can not, let's say, bowing and having like the belly to go down. We also try to look into how to make the electronics work a little bit like in an interesting way. For instance, when we hit the end, we do something, we turn on an LED, we do something else with something called interrupts, which is we're moving all the time, but when we hit, then we do something else, but not because we are constantly reading the sensor, but we do like what is actually called interrupt, which was something we explored here. We built several prototypes, we explored laser, 3D printing, whatever, and I think that's the purpose of it. It doesn't have to be like too complex. Now we could build a complex machine. We have support to do that, but it doesn't have to be like something super, you know,
Yep.
Can be anything.
Well, okay.
So yeah, but it needs to have a structure, it needs to have movement, you have to control the movement, and it has to work. So there should be a final result of what you expect.
Okay. And the thing that controls the movement, it doesn't need to be made by us. It could be something that we buy or whatever.
No, we have them here.
Or we take
give them
from
to
you.
you,
Yeah.
or
The electronics.
Yeah.
Like, and that where comes like what the machines talk. Just have a 5-10 minute break.
yeah. But we're not gonna see some machines, or we see some machines and then we talk to that. But we have a break before. So break machines.
We need to finish at 1 because the time schedule changes.
Okay.
The classes start at 2. So we can leave either the Gcode for tomorrow and they can practice, or
Or maybe we could do like, do you mind if we do the break while we see the machines?
Yeah, like an easy.
Like easy, it's not gonna be like so hard but then we go around, we see some machines, some examples. If you want to go small, you can go. But then in 5 minutes, 5-10 minutes, we're back and we do Gcode. You want that? Yeah. Okay, let's go.
connect it with my phone. Hola. Okay, let me change the camera. Oops. So let's go to see a little bit some machine examples and how they're built up. So, está apagada. So, for example, these guys, or los bearings, no? Sí. So here, this machine has the rack, and this basically is a belt that is just to protect from the dust, to don't lock inside the gear. Then we have, this is the linear bearing that in this case is a square profile and it's just hidden here. This machine is cool that in the way that we have 2 racks, that is one here and one in the other side to keep even movement. That means that we need to use 2 motors. This machine doesn't have 2 motors, uses 1. It's exactly in the middle of the axis. Actually, here we can open. This is for maintenance, and we can see the motor is just in the middle, and we have a big central axis with the gear touching
On the bearing. You see it here, protected with a rim, so that in this side is for the axis and on the other side. And basically, so you get how we move the motor there. Just this pinion is connected to something else in the middle, I guess, and then another one here. Yeah. So you control one motor, one movement. Same on the other one.
el que sí, we can go on top of the machine. Estás. Bueno, sí, subimos. Yeah, here we can see you can move in here. Don't worry. As long as we don't jump all the class in top of the machine. So here we can see that we have the linear movement. The Z needs a lot of strength to don't bend. Actually, in here, for example, we have double linear bearing, quite huge, and the bearings are inside, and they have 4. They have 2 here, and 2 here, and 2 here. Probably it has 3. We don't see them to reinforce a lot the side movement of the axis. And we have the big motor with a reduction gear, because this axis is moving in small amounts, but needs a lot of force to push it. As this is really heavy, usually the Z axis, we can see from the bottom. We don't see it now. But we have a spring that is also helping to keep the position, because this motor is quite heavy. So actually, instead of having everything held by the motor, we have also a spring helping to the motor doesn't fall when we switch off the machine.
You have to change it every now and then.
What?
The spring.
Yes, but that means years of.
Oh,
um. For example, this other machine that is a Press 6 is a way, way, way lighter machine. It's for light tasks, not for heavy tasks. So we can move it. ¿La puedes empujar un poco? Sí, sí, dale, a ver. Dale. This one, for example, we can move by hand. That's already is a huge difference. So in this case, we have also the linear bearing here. And the movement of this machine is we have here a motor that the motor is quite thin, as you can see. So actually it's a thin motor, but we have a lot of gears to make a reduction. And then we move with a belt that is just here. Yes. So we have the belt coming up, and this is a linear bearing. And here, this is actually we don't see it a lot. Can I switch on the light? No. Oh, here. We can see the belt coming inside. And for example, here, this is a linear ball bearing, ball screw. So we have the chamfer that is round for all the bearings. Actually, only this shaft is quite expensive.
one thing that we didn't talk about is that the machine needs to know where it is. We will see later that it's something called homing, so that we find, let's say, the origin of the machine. But at some point, the machine needs to find itself. When you turn on the machine, it doesn't know if it's here. I just moved it, and no one told it. Powered off, doesn't have any memory. How do you do it? Either you go and do the process of homing to a safe location, let's say, your home, and then normally this is here and here, and you need something that helps you when you got there, something that we call stop, which is just normally a switch. These switches,
Okay, you know.
I don't know if there's anything here. There's one there, and there's another one here on the side if you want to come. So this one axis here has this little end stop in there that when it gets to the end of the rail, it gets pushed by this element in here. If you come to this side, you'll see it. So you see that there's just a normal switch that pushes, and you get there, and you know that you are at the end of this machine. And you have the same on the other side, so that you don't hit. And you see that it's asymmetric on the other side. If you can mark it, just se puede la chaveta ahí está. You see that it's asymmetric because the end stop is here, and you have to save the amount of this distance, so you don't hit on the other side. So you do the same. This machine is very like old school, let's say, in that sense, because it just has this type of things casted on the machine. Other types of machines use more complex mechanisms, like that one. How does it work?
Here we have a magnet that when the The brick comes up, seals the magnetic difference, and activate it. And on the top of that one, we can see that protector. Yeah, the white part are the two magnetic. So the one is the pulsar. Sorry.
If you don't know, especially in CNC machines, if you don't know the size of the stock, you need to put something that you know the height of, so that your machine touch your end mill touches, and that way it goes through. And that can be done either with this type of thing or like the previous one in software, which has an electric plate and conductance between the end mill to an electric plate that you put on top.
Closing the circuit.
Closing a
Okay.
circuit,
Touching
like
two
making
cables.
which is the same as this, but with a
Un poco más pegado.
What about the mechanic thing? So we're saying, this is for the, but for the
these other ones are these elements that when this gets here.
And also, if the machine is well assembled, especially like no electric, doesn't have a lot of electrical noises, because it's measuring difference in magnetics. If the machine produces a lot of electrical noise, can self-confuse itself. So there are also some machines that they use optical one, and they use a laser beam to know if we have passed. Like, you know, the car entrance or the automatic one, they use kind of similar system, or just a probe, a slightly more complex button that goes up and down automatically. Let's go on to other machines to see what is the difference. Sí. So again, this machine is supposed to be fast, but the problem is heavy because we have the laser beam and everything, so we need to move a lot of mass. What system we have here? Again, pinion and rack, just because we need to move a lot of mass, and we need to make it resistant for like more industrial environments. So it's a solution that you usually go when you have open systems. Also here, for example, what is the end stop? One of the end stops is this guy. This one is optical. This is has two utilities: end stop and at the same time presence detector. So if you get too close, the machine stops. That is these guys that we have a laser beam just going to yellow, from yellow to yellow. So if they measure the distance and the time it takes to fly the light between both elements. In these guys, what are the movements we produce with laser cutters? XY movements really fast, and Z movements really slow and accurately. Here, accuracy in the Z matters a lot. So actually, when you open them up, es que la tiene esto escondida esta máquina, tío. Aquí. Here, for example, the Z moves with a ball screw, because we have 1, 2, 3, and 4 ball screws. to move all the platform down eventually, and with small movements and really control movements. Meanwhile, the X and Y needs to be really fast. So actually the belt is hidden in the profile. This is a Y profile that is like coming here and coming in the back. And we have the motor hold exactly in the same profile with teeth. Okay. More machines. Let's go into 3D printers because there are two big differences between 3D printers. ¿Qué bien te lo pasas? So, sorry. For example, these are Delta machines. The Delta in general, you have a smaller motors for moving the both axes, and the 3 motors make combination for X, Y, Z at the same time. So that means we need to produce smaller movements, but we need to do them faster because a small movement in here, in this one, implies X, Y, Z at the same time. So we need to make faster movements, but accurately, because just a little movement of this guy moves a lot, we went through again linear rates. And actually, this is what you usually want to go for. What happened? These guys are usually way more expensive, the linear race. Linear race with linear bearings. As we want to move fast and we don't have a lot of mass, we can go with belts. Actually, this is a really long belt distance. In this case, might not hurt to go to a slightly wider belt, but just to keep the cost down, they have a thin belt. So one of the great I will try to do this one is use thicker belts.
So you just put?
What?
You just put the belt and then the mechanism.
But this is just for sliding, to keep the linear, the line. So this is in charge of keeping everything in the line, and this one is of actually getting the movement. This is the same that pulling a rope. So it's pulling the rope from this direction, and if not, it's pulling from this direction. We have a bearing here on the top to pull up. So pulls and pulls. And you see this little tension, this is a spring. Ideally, we should not have this but it helps a lot for keeping the belt in tension. Ideally, you should have a secondary system that is a ball that pushes the belt a little bit eccentrically. Cheap solution, and it works well for 3D printers because they don't have a lot of mass, is we have a spring that is quite springy, it's quite strong to keep the belt in tension. What happens if you pull a lot? Let's say you use this for milling, means making a lot of force, the spring elongates. That will not be good. For example, this is not a solution you could use for something that you need to push with. Prusa, for example, just on the hardware is completely different. We have the dry axes that have linear bearings on the bottom that makes it slide really well, and we have the belt also to produce the movement. Will be the same, but this one is linear, a cylindrical one, and this one is a square one. Cylindrical one versus a square. What will be the difference? A cylindrical one, you can make this movement, but you can also make this one. So you have one motion that is out of control. We can also rotate like this in the main axis. It's a cylinder. What happens? If you have two, you can connect them and avoid the rotation. Meanwhile, these guys, they automatically lock in place because they are square. They don't allow rotation on the axis.
Like that too?
No, but if you have a cylinder here, we can rotate it. Sorry, we can rotate it like this, just like in my hand. With 3D printers, we move X, Y really fast. So we have belts and linear bearings in the X and Y. The Z just moves a little bit every time. That's why we have again, threaded screws. And here you can see there is only one nut. We have actually all 3D printers use this system because it makes cheap and it's not improving this, increase a lot the cost. So actually the nut, what would happen? The Z is not moving up and down all the time. Actually just moving a little bit. And we have something that is gravity. So actually it's being pushed because this is heavy, it's being pushed all the time to the bottom. But in case that you are really printing in 3D, that is printing, moving the Z all the time, that might happen, you will have a lot of backlash. Actually, you can see from the printing quality that is set. A ver, algo impreso. Tenemos por aquí. Yeah. Apart from in this guy, like the print quality, etc. But this is the banding. This is actually because of the backlash of the set. That the rotation of the screw is not exactly even in all the rotation, and the nut has a little bit of play. So if we are pushing more plastic and the plastic cannot get out, the Z is moving a little bit up. It's moving the whole bridge up because the plastic has more force than actually because we have a little bit of play. So actually that's the banding, and it's caused because of the vertical backlash of the Z that we have in the 3D printer. So to avoid that, first calibrate the printer, and second is like put an anti-backlash nut on the Z, or try to replace your threaded rod because it might be too used and has more tolerance. These guys, one of the reasons why 3D printer has become cheap, instead of having linear bearing, we use it's the same but in big scale. Producing linear bearings is small, we need accuracy, it's million metal. So what they have done is they put a bearing inside a roller, and the roller uses the profile. So actually it's using the whole profile as a linear guide. Actually, it's a really smart solution, works well for the accuracy that you want in these machines. What has a problem? That is basically it's a plastic rolling a surface. The roller, the same as the tires, they get wasted, so you need to replace the roller. So they get wasted. So after like 1-2 years of use, depends on the amount of power, you need to replace all the wheels that are inside. And also there are different materials for the rollers. You have like this black generic plastic. You have Delrin that is a stronger, less frictionless material. So actually this come in like multiple materials and formats. What is the limit of the accuracy of this machine? First, how straight are these profiles? That usually they are not microns accuracy. They are like 0.5 millimeter accuracy. Second, the wheeler. That is a plastic part. Usually it's not that machine as a metal. So it has reduced accuracy. That's why this machine become so cheap, because reducing a lot the manufacturing costs and cost of like accuracy. So they are good platforms, but you can upgrade them a lot actually to make them print really, really well. And for example, this machine, as simple as just for the size, this machine uses a 2040 profile. It's good in this direction, but really bad in this direction. Actually, the first upgrade that you will need to do to this machine is to put a connection here, a triangulation. Actually, it doesn't bend. This is a really huge cantilever. Or increase the profile. For example, this one is a way stronger frame that is 30 by 30 profiles. So the frame is way stronger. And uses again belts for producing the movement, and uses double set for the axis, like threaded rods. But again, to keep down the cost, is a simple threaded rod. It's not a ball screw. Oops, sorry. Meanwhile, this machine, for example, you see, is the SLA. We only produce one movement. It needs to be really accurate. That's why we have actually 2 big linear axes, square ones. Actually, the whole platform that you see on the back, this and this, actually each bearing is like that. We have double ones, really huge, to have a lot of stability on the Z. And for the movement, this one uses a threaded dot. So you have two really big bearings. You can go with a threaded dot and not with a ball bearing because you already have a really sturdy system in the other side. But ideally, you should go also with a ball system in the set. Because as you only have one thing that is determining your whole quality, you want to make it good. And for example, this so silly, but this spool holder, just to help the spool move slower, we have a cylinder that is sitting on some bearings to reduce the friction and make them rotate really nicely. Yeah, let's go to the room in the classroom. Yeah, here. Yes.
Okay, just one thing. Before we jump into the how do we talk to machines, I want to make just two very quick comments. The first one is, sorry? Yeah. So first one is about the difference between the motors that we use in machines. We haven't talked about this much, and we will talk a lot about it in outputs. But basically, you see something very similar between this one, that one, this, and this one here. These are all stepper motors. Okay, they have a more complex connector than just two wires. Why? This motor here only we have this shaft. You see that is rotating inside. Pues mover un poco la cámara. This shaft that is rotating inside because we apply current to these two poles. This is a DC motor, so we put DC voltage in, and we create a magnetic field that basically makes this rotate. Okay, the more current we put, the faster it rotates. The more voltage we put, the stronger it is. Okay, these ones operate in a different manner. They just don't have. ¿Dónde está el abierto? Yo estaba buscando. These ones operate in a different way. I will
imagine two motors, two DC motors combined, and one is fighting each other. So if both rotate in the same direction, you move. If one is rotating against the other one, they don't move, locks the position.
Yeah. So in here you see that there's a lot of coils, and by the way that you actuate those coils with respect to these little metal parts that you have on the axis, you can manage to have a very precise step. So a little bit of movement and a little bit of movement every time. If you see in the GIF that he has, and you can pass this along, you actuate every time coils, and then that makes a little realignment of the axis to make a little movement each time. If you put a lot of small magnets and you actuate the coils, let's say somehow in a smart way, you can achieve per revolution 128, 256, etc., steps. That's why these are called stepper motors, because they go by steps, and you control them with more cables, not just 2 cables. You actually have to control the coils, and you need a special piece of electronics for that. That brings us to control electronics. We will.
I'm gonna leave words. For each axis of coil, you need one cable.
No.
No, it's basically you have, imagine that you have one DC motor is a coil, and you have another DC motor. So when this one has magnetic fields in this direction, and this one has in this direction, you can move because one is fighting each other. If you control and you just do in one direction and you move back into the other direction, just move one step. So what happened? This is coil. This is the same coil. in this order.
It keeps one technically.
It keeps one. So actually, this is coil. We call it 1A, 1B, and the other coil is.
For example, in the GIF, it's just 2 by 2. Yeah.
No. In all the supermotors is 2B. The GIF is not exactly accurate. Actually, when you push this one, you also push. So actually, you are activating, how to say, this guy and this guy, or this guy and this guy at the same time. You activate cross patterns. But to make it simple, like you simplify like this, the visualization.
Okay.
Now, as you can imagine, to control that is not, let's say, a trivial thing. So you need a piece of electronics that can support that type of control. We'll see in outputs how we do that, but basically just keep in mind that for controlling stepper motors, you need something that is a driver. We call them driver, and normally we call them either stepper drivers, step sticks, drivers in general, that can be as big as that one for very big motors, like the ones in the CNC, or big motor sizes, or that one over there. This one is more like 3D printed world. This basically does chopping of the current and timing of the coil and in those pins with inputs from the microcontroller, from your AT timing or your ESP32, etc. This one does the same, but is able to handle a lot of more current. At the end, imagine that what you have to do is put current, cut current, put current, cut current. And that, for doing that, you need to be able to open and close current on big loads of current if it's a big motor. So, of course, these things get hot, and that's why you have this little radiator. And these ones here are like big pieces of electronics to control things. Now, these other ones, you can control them with just 2 cables, but you use the technique we talked about, and we will see in output, called PWM, which is you just have an average voltage based on the amount of time that you're on versus the amount of time that you're off. And you just put 12 volts, but with on, off, on, off, on, off, and you regulate the speed because of that. All that is put into an electronics box that runs a little piece of code inside. That piece of code basically understands how the machine is, how the machine is built, and takes something like that we call like a generic file, Gcode file, or a script of the instructions that we want to give to the machine to move, and translate it into movement of the machine. This code knows how big this axis is, how big this axis is, what is the ratio for every turn that we do here versus the amount of movement that we do there. And what we write is not actual movement of each of the motors, but what we write is something somewhat generic that makes an abstraction of the machine and the electronics. And we just write, let's say, a script of movements relative to the actual surface or actual volume that we want to move on. So we say, imagine that the abstraction layer is, I want to move from here to here. And then I want to move from here, doing an arc through a certain speed. We don't control each of the motors separately, like writing code in each of them. What we do is that we write actually the movements that we want to do. We send them to this piece of electronics, and then this piece of electronics controls the machine. Is that more or less clear? What we're going to understand right now is what are those instructions that we have to give to the machines so that they can make those movements. And this is the last part that we're going to make a quick introduction now and maybe talk about it more in detail tomorrow. That is called Gcode, let's say. So when you hear Gcode in 3D printers or in this type of machines, is the code that basically gives the coordinates to the machine to make the movement, and then you put that, you send that here, either you put it in an SD card or you send it via USB, and then this translates that G-code into actual movement of each of the motors by controlling each of the parts. Okay.
All these machines, there are two types. I'm just going to mention a little bit in the industrial field. All these machines are called open loop. It means the electronics gives the information and is sent to the drivers, and the drivers sent to the motors. That means only one direction. The motor is not giving any information if it has actually moved correctly. That might happen sometimes. The 3D printers are like it crashing because it doesn't know exactly what it is. So with stepper motors, that's what happened. Basically, it's a complex coil to make the movements. There is another type of motor that is called the servo motor. The servo motor is might look similar. For example, this guy seems similar to this one, and this one looks similar. Actually, this one is just shorter. This one is a larger version, but this is a stepper and this is a servo motor. What will be the difference? This guy has electronics inside, has the driver embedded, and also has an encoder. Encoder is a little device that reads the position. So actually, the driver is at the same time giving the information, but getting feedback on the total amount of rotations that the motor has done. So actually, that's what we call closed loop. Like we are giving the information on the amount of movement, and the motor is telling us if we have actually moved. Obviously, that is a way better system because we have always control of what we are doing. If the motor has not moved actually to the good position, it will still try to reach that position because it has not reached the target. So it's actively tracking the position until it finishes the position. What happened? This is a slightly more complex piece of hardware, and also implies in general it's always better. What happens? The control is more difficult, and especially it's way more expensive. This is a servo motor, a NEMA 23, cost, I don't know, like 20 with 160 euros. The servo motor is 300 euros, and this is the cheapest one you can find. Like it's a super Chinese copy of another. This servo motor is not completely a full servo motor. Like servo motors right now is like from 1,000 and up barrier. So what is the construction inside? Yeah.
The servo motor knows position or not the related movement.
No, knows the position.
So
the position of the rotation of the motor.
Yeah. Okay. For example.
Exactly. Servo motors might not need to home. So as inside you have like programming modes, and you have custom firmwares just to control how the motor moves. So actually they need just a completely programming on their own. It's not you just connect it and that's it. They are not plug and play. You need to program them to make them work how you want. So for example, as you know, the total amount of movement, we also control the total amount of current that they're consuming, and you can establish a limit. For example, if the motor is 10 amperes, but you want to keep it safe, you say, if you go above 8 amperes, switch off and show alarm state. You can program it. They are, let's say, smart motors.
We need the other part of the electronic that you gave us before, or it's directly CPU to that.
For the servo motors, this one is a servo motor with embedded electronics.
Okay.
Servo motors can have also external electronics. This is a servo motor driver. Looks similar to the other one, but has like 25 more connections. So basically, it's a stepper motor. Inside, how it's built inside, could be similar to a stepper motor. It's more complex. It's closer to a brushless, and has an encoder to read the position plus electronics. And usually, as they are industrially grade, that they are more complex, also it means like better build quality, better bearings, seals. Like in general, like as you go to more expensive hardware, they already assume that you need some like minimum industry like quality in general, and they are really good quality. Like I don't know. For example, the dog of Boston Dynamics that they play. Actually, it uses force servo motors for all of them, because also the servo motors in general, they have like 3 or 4 times more power per weight ratio than stepper motors. So from the same package, they are 4 times stronger in general. Huh? Because how the coils are inside is not exactly a stepper motor. It's what is called a brushless. That is another leak that for machine in general we never use.
We will start maybe with all that.
Yeah, like that's changing because brushless motor, a type of motor that in general is quite complex to use and have control over them. But nowadays, on like software has moved so ahead, and electronic wise is moving so ahead that it start to become controllable to using machines. Actually, the guys like Victor is using them to make the roller gimbal on the cable bot using this kind of motors. Before it was difficult to control the position, now it starts to become easy.
But
Said that? No.
no, just that. And so this is for motor, and don't worry, we will have an output class for motors in huge depth. For today, just remember that these type of motors are different than these ones. These can control steps very precisely. That's why we use them for controlling axis. And this one just didn't need to rotate. Servo motors, you need them either because you need a lot of torque or because you want to control on maybe on a certain rate of rotation. An actuator that, for instance, like in that one we had that cleaned, deployed and cleaned the bed, and that just does a movement like from 0 to 90, or some other applications like these big ones that are a little bit out of scope for this machine with, let's say. But don't worry, in output we'll talk about them a lot. Now, so we've been talking about all the components, let's say motors, etc., and that we said that this basically just expects instructions in the form of coordinates and certain type of scripted commands for it to do certain things. For instance, we don't tell the 2 pins of the microcontroller to turn on this motor by putting current in here, but we actually say turn on the spindle. And then we just tell that to this electronics, and it turns on the spindle. Then we say move to X0, Y0. And we just said that, and then the electronics take care of moving this axis and this other axis, and the machine goes here. But we just say move to certain position, do it at a certain speed, follow the certain path, but we don't actually control the pins of the microcontroller ourselves. That is done by a firmware that runs inside of here. What we're going to talk about now is what are these set of instructions that we can give to these electronics to do this movement, and that is what we call Gcode. Okay? Yeah.
These firmware are Gcode interpreters. So they read instructions and they associate with certain movements that are predefined. So basically you need to upload the firmware or the code into the machine. That is the firmware. So it knows how to interpret your new file that you are sending. There are 2 big variants right now in the open source world. That is Marlin, that is for 3D printers in general, could be used for other applications, but in general it's like has a lot of options, a lot of capabilities, like multiple capabilities of everything you can imagine, but it's not really robust. Like for CNCs, that a machine that they usually don't need a lot of capabilities, but you need robustness, you use GRBL at the 2 standards, like firmware interpreters. For CNCs, in general, you use GRBL. For 3D printing or laser cutters, you use Marlin. But laser cutters could be between GRBL and Marlin both at the same time. For other machines, that will depend. You need a machine that just makes movements, GRBL. You need a machine that makes activate lights, puts fans, etc. And you need a lot of things, you use Marlin. It's like more customizable, let's say. Gcode interpreters read Gcode. That is basically is the standard for sending commands for any fabrication equipment. 3D printers, laser cutters, CNCs. As you know, some machines use their custom G-code style. For example, Roland is that they have developed their own custom G-code, so they only reach their own proprietary type of file, just because they want to enable some special characteristic that is not enabled by default by other interpreters. So when you launch a file, usually it looks something like this. And you have a lot of commented things that is actually just human information, information for the user. And we have other type of things that they start usually with an M or a G. In general, M is a command to send activation or deactivation of things or configurations. And G is a command to actually produce something, a movement or an activation.
What is S? Speed? I don't know.
Where is S?
Yeah.
S is not a speed, it's a level of the signal. So for example, M190, in this case is temperature, set to 90, to 60 degrees. If it's a fan, will be set to 150, will be 150 PWM. That is a signal that goes on to 250. So it's actually 70%. It varies a little bit, but let's not get too messy. So we have G commands that actually is motion and M that are action. And then we have the movements that is X, Y, Z. If you have a machine that is not 3-axis, it's at 5-axis will be X, Y, Z, A, B. If it's 6-axis, C. If it's 7-axis, D. If it's 8-axis, E. In general, we just stay with the 3 ones. But for example, with the robots, you have like X, Y, Z, A, B, C, D, and the custom rotation ones, R1, R2, R3, R4, R5, R6, R6. So it's a longer format of G-code, so it's not called anymore G-code. It's custom for each robot. So let's say, what are the basic ones? For example, G0 is a command that is G is move, 0 is in general used for moving fast, not doing anything. Let's say a 3D printer just moving to a position without printing. So G0 coordinate X, Y, Z, whatever you want, and it will move to a position. G1 is the same, but in G1 you specify the speed that you want to move. So G0 and G1 does the same, but in G1 command you specify the speed. So for example, here we have G0 move to X12. It will move 12 millimeter on the X axis. G0 move at this speed. You can also specify the speed in G0, but it's something that usually, like, these are standard in communication, you don't want to do it. And you have G1 move to this position, X90, Y13. And usually the F, that is the speed, is the feed rate that you might remember from CNC. Is the feed rate, is the moving speed. Communication? Not too much, no? No. So usually the G0 is what is called rapid linear movement. It means transfer movements. When, for example, last week you were cutting, the machine was moving in the air, was moving really fast, no? So that will be a G0 movement. When the machine is cutting, it's a rapid movement that is just cut, like, and move, and the setting speed that you establish, that is the feed rate that you establish. So that's a standard. You can use G0 to produce cutting movements, yes, but in general, so if you make a file, he understands, use G0 to not do anything, just move in the air, and G1 to actually do something, an action in your movement. You can establish relative or absolute coordinates. We can establish new coordinate systems in commands. And you do that by using a command that is called G90 or G91. G90 means we use absolute, use the origin of the machine. G91, it means use a relative coordinate that you have to have previously set up. We have also commands like G20 that is telling to the machine that your file is in millimeters. You will say, what other kind of units we have? Inches. G21 is to make the scale up of your machine movements in inches. Actually, the list of commands is huge. That's why we have Gcode libraries. And it basically is a web page that is a dictionary, and you go like G35. Okay, this is this, and give you instructions of what is everything. Like we remember some Gcodes, but we don't remember all of them. Like I remember, for example, the most standard one that is M106, M107, fan on, fan off. I don't remember, for example, how to put the temperature of the extruder. I think it's 104, but I don't remember. I'm not sure.
We don't need to know this by heart. You can just have a
Exactly. For example, the most easy guide is the Marlin Gcode guide. First link, Gcode Marlin firmware, and boom, all the type of commands that you can send. So for example, you find command G92. G92 is actually set the position, and it's explaining you actually how to use it with the example. For example, let's say you want to set up your file in inches. Inches unit, G20. G20 sends the units to the machine to work in inches. Tomorrow, we recommend you to look a little bit at this. It's in the docs. It's in the clubs, make club Gcode. This year we have changed a little bit the structure. Tomorrow we will play with that machine, and you will connect with your computer and send manually Gcodes. And the point is to actually play a game with sending manually Gcodes.
From which? How do we send Gcodes? From which software? From
you can send from Arduino or whatever.
Oh, okay, cool.
Like we can send from the multiple things. We will see tomorrow the option.
And you can connect wireless with it. Okay.
So what's like the actual writing on their own keyboard instead of like using
A standard one.
some kind of software and translate your, for example, 3D models into keyboard?
Well, that's what you would do in production, but here we are also learning the basics.
For example,
So you're gonna do some manual work on to sending manual Gcode. You're also gonna make some files by yourselves to make that machine move the whole thing, but you don't want to send one by one. But the point for this one is just to get to know, be a little familiar with Gcode instructions.
so
You will send some manually, just 10, 20, something like this, not 500.
in industrial environments, you program automatically the code most of times. If it's a repetitive task, they do it manually to make it optimized.
Like with massive control on the way it's done.
Exactly. So for example, in your case, the CNC you made with RhinoCam. RhinoCam is a processor that produces the code for your machine. All you have seen in the CNC that shows the code. Why? Because something bad happened, you know exactly where to stop. Or you can introduce commands. Meanwhile, if you want to, you cut 1 hour. But if you're making a production of 14 hours and you need to go to the restroom and your machine by somehow doesn't have a pause, you can send that your command in live pause. That is a G4P500. That is pause for half second, for example. Or it's really important to actually know how to use the commands because you can debug what happened first. Second, you can upgrade things and change it. You can introduce change on the go. That is a really important thing. You always produce use post processors in general. 3D printer, Cura is a post processor for 3D printers. RhinoCam is a post processor for CNCs. The Rhino plugin of the Cut Studio of the vinyl cutter is a post processor for vinyl cutters. But you are able to actually do the same. So for example, just case study application. At home, I have a 3D printer. I do a lot of experimental stuff. When you move your machine with the joystick, like the plus X to move it, what you are doing is G91 set relative coordinates. G92 establish this as origin of the absolute coordinates, and you said G1 extend. Each time you click, it's G1 extend, G1 extend. So actually you are able to send this automatically. So, for example, for this machine, we have a custom script to make the machine self-clean itself. That is code just by sending coordinates. And this is compiling like 20 lines of Gcode. So you're able to make a lot of customization, change things on the go, and tweak also how the machine works, because you can send a command before another one. For example, you have seen that the 3D printers right now, they hit the bed, then they hit the extruder, and then they print. No? You can actually, if you know this, how to use Gcode, in Cura, you can configure to hit the extruder and the bed at the same time. So actually you save 3 minutes. For example, my Cura is configured like that. I hit both things at the same time to save time because I don't want to wait. Or hit first the extruder and then the base because this one takes more than this one. Or switch on the fan meanwhile it's heating, or home at the same time that it's heating. You can change how the machine behaves on its own. Or for example, you don't see it here, but machine says before using them, you need to warm the spindle for 3-5 minutes. Like it's a good workflow. You can introduce that in all your files. And basically it's 3 lines of code. Is T1, tool 1, M4, M5, that is switch on the spindle, G4, P5, no, 5,000, 15,000, that is 5 minutes, more or less, slightly more, is 7 minutes, and M4, M5, M8, that is switch on the spindle. And then you will put your file. So basically it's open your first lines and copy on top. Don't know if I have Gcode around it, but here, for example, simple and simple. And for example, G90, relative coordinates. G64, I don't remember. Probably, I think it's flooding configuration. Switch on the flooding of the machine. M7, check that the motor is off. M8, turn the motor off, just in case. G1, select the motor. S20,000, set 20,000 RPM of the motor. M3, now that we are sure that we have turned on the motor, we switch on the motor. Why? These ones are mandatory, M7, M8? No. It's a good workflow? Yes, because maybe the motor, if you switch on the motor and the RPM are crazy, you can damage the motor. So first, turn off the motor, the first thing on the file, and then we manage the speeds. Then is G0, move 50 millimeters up, then move to position GX220, Y80, move in the air. We don't say the speed, it's gonna take by defect the machine speed because it's a G0 command. And then we have our movement. That is, move in the same position, -10 at 3,500 millimeters per minute. Move down 10 millimeters. So it's important to know this because if your file fails in the first 5 lines, you need to know why it fails. If your file is a Gcode, you didn't export to the good machine, you did export to the good machine. So the first thing is, if I see that my file just do something weird out of scale, the first thing I check is, okay, is my file in millimeters? Do I see a G20? No, because this machine actually doesn't accept G21, so we don't need to set it up. But in like 3D printers, yes, it does. If I don't see a G20 and it's doing things 2.5 times bigger, first suspicious guy is the Gcode. Yep. So here we have some graphic examples for actually how to produce movements. We have G0s, G1s, and then we have G2s and G3s that in general, we don't code them manually. They are too complex, but they exist. And some reference. So it would be nice if tomorrow you can at least read a little bit the commands that are in this page. That this is the basic ones. Okay? Tomorrow we will go hands-on and play and assemble the machine. Yeah, any questions? apart from a lot of questions?
No, I think when we start doing the machines, we would have
A lot of questions.
too many questions.
Okay.
So that would certainly-
Hmm?
So we assemble the machine.
The small one, like the orange one.
Oh,
Remember that the class starts at 2 today, because we are still with the time delay change. We didn't change the summer schedule yet. Okay. So see you in 1 hour, guys.
I think you're, yeah,